Hello. My name is Kamil Valchuk, and today I will present a brief summary of my master's thesis for which I received a master's degree in physics at Adam Mickiewicz University in Poznan, Poland, in May of 2000. Adam Mickiewicz University is one of the top universities in the Eastern Europe. Its reputation has been founded on tradition lasting over 400 years. It was established in 1611, the outstanding achievements of its academic faculty, and the attractive curriculum offered to students mainly from European countries. According to the U.S. News & World Report from 2024, Adam Mickiewicz University, commonly abbreviated to UAM, is ranked number 4 in Poland, number 340 in Europe, and number 935 in the world. Further, by taking into consideration individual subjects, Adam Mickiewicz University is ranked number 657 in physics, with the overall score of 33.8, number 471 in mathematics, with the overall score of 27.7, and number 602 in chemistry, with the overall score of 47.0, on the list of the best universities in the world. My master's thesis was written in the Department of Nonlinear Optics under the supervision of Professor Richard Tanas, who was the chair of the department at that time and taught two-semester course in quantum optics. The title of my master's thesis was formulated as Quantum Fluctuations in Optical Processes. Quantum fluctuations are byproducts of the quantization of quantum fields, while the procedure of quantization results in discretization of accessible energy levels from the whole spectrum of energies and introduces particles and antiparticles to the quantum description of reality. It turns out that the physical vacuum is not an ontological nothingness, but it is consisted of a combination of intermingled and quantized fields, where every field is represented by an infinite amount of quantum mechanical harmonic oscillators. The excited states of those oscillators are viewed as particles in an empty space, while the ground states of those oscillators describe absence of any visible particles and are characterized by non-zero energy, half a quantum. This zero-point energy is related to quantum fluctuations, also known as quantum noise, and according to the concept of the wave-particle duality, quantum fluctuations may be viewed as an existence in the empty space certain modes of vibrations. Those specific vibrations may also be represented by the repeating processes of creation and then fast annihilation of virtual pairs of particle-antiparticle. Since the physical vacuum constitutes an arena for all the physical processes, there must be observable effects of the interaction between vacuum and any material object placed there. In my thesis, I presented the systematic theoretical studies of the influence of quantum noise associated with empty space on some chosen phenomena in quantum optics. One of the considered problems was related to spontaneous emission, where the atom in the excited state relaxes to its ground state and emits photon, by a combined effect of interaction with vacuum and the radiation reaction self-interaction process in which the virtual photon is emitted and then reabsorbed by the same atom. It leads directly to renormalization procedure. Another analyzed problem was the Lamb-Rutherford shift, where certain energy levels of atoms are shifted due to interaction of the bounded electron with quantum noise of electromagnetic field. The third analyzed problem was the so-called Casimir effect, in which the spatial confinement between two uncharged plates limits the existence of vacuum field modes in between these plates, while the space outside the plates enables spreading of any of them. The unbalanced outside modes generate non-gravitational attractive force between two plates, which is inversely proportional to the fourth power of the distance between them. This Casimir effect is crucial in determining stability of nanoscale capacitors. Obviously, the vacuum quantum states satisfy the Heisenberg uncertainty principle. However, it is possible to reduce uncertainty of one variable of the vacuum quantum field, such as amplitude, on the cost of uncertainty of the complementary variable, such as phase, generating the so-called squeezed vacuum state. As an example, I analyzed the generation of the second harmonics, where portion of photons passing through a nonlinear crystal medium are coupled together and form new photons of doubled energy, simultaneously squeezing the vacuum quantum state. The relationship between squeezing and photon anti-bunching effect in the generation of second harmonics were also discussed in my thesis. Squeezed vacuum states can be used to reduce an amount of noise in precisely designed optical experiments that could be used for detection of gravitational waves. The first direct observation of gravitational waves was actually made in 2015, when a signal generated by the collision of two black holes was received by the LIGO gravitational wave detectors. My theoretical results were presented mainly in the form of analytical expressions derived from the first principles using the quantum mechanical formalism of second quantization. The knowledge included in this thesis brings us closer to better understanding of the role of physical vacuum and its quantum nature in optical processes. Quantum noise is also important in astrophysics and cosmology, where zero-point energy is sometimes identified with the actual value of cosmological constant, and seems to be crucial in explaining the mysteries of an early-stage inflation of our universe and maybe even the origin of mass. Besides, in the literature, the concept of quantum noise was also used to describe the Unruh effect of background heating due to acceleration of reference frame and Hawking process of the evaporation of black holes. Thank you so much for listening. That was my presentation with a very superficial explanation of the material included in my thesis. Of course, the devil is in the details, and a thorough understanding of this topic requires the use of advanced computational techniques developed within the framework of quantum field theory. If, like me, you are interested in specific topics associated with modern physics and philosophy of science, then please subscribe to my channel and hit the bell, so you can get notifications of some new material uploaded there. If you enjoyed this presentation, then please hit the like button to give me motivation to work on other presentations. Also, don't forget to leave your comments below. Is there any specific topic in physics that you would like to understand better? I would be happy to help and prepare another presentation on the topic suggested by you. Best of luck with your conceptual understanding of physics.